Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to answer a question I commonly get, which is, what is the difference between neural networks and deep learning? I hope to squash some commonly held misconceptions, and I hope this helps you gain a better perspective on deep learning, machine learning, and neural networks at a high level. The first misconception I'd like to talk about is this. A lot of people assume that to do deep learning, you have to be using convolutional neural networks and recurrent neural networks. This is very wrong. First, if you look at the name, convolutional neural networks, we see that it has the term neural networks. We don't call it convolutional deep learning. Nobody says convolutional deep learning. We say convolutional neural networks. Okay, so studying convolutional neural networks and recurrent neural networks means you're studying neural networks. Of course, it also means you're studying deep learning simultaneously. But here's another reason why that's wrong. Both of the famous CNN and RNN architectures were actually invented in the 90s. So for RNNs, the relevant building block is called the LSTM. And if you want to look up the original paper, I've listed it here. And remember, in the 90s, the term deep learning did not even exist. So to say you must be studying CNNs and RNNs to be considered as doing deep learning is just false. CNNs and RNNs were invented long before the term deep learning ever existed. Another misconception is that to be studying deep learning, the neural networks you're studying must have more than one hidden layer. This is, of course, also false, since neural networks with more than one hidden layer also existed and were researched long before CNNs and RNNs, and hence also predate the term deep learning. The fact remains, in order to understand how a neural network with multiple hidden layers works, you must first understand how a neural network with one hidden layer works. You simply can't skip this critical step, and it deserves a significant amount of attention, whereas adding more layers, once you already know how to deal with one layer, is significantly easier. So what is deep learning? It's actually a relatively meaningless term. It's a buzzword. Someone started calling the set of neural network architectures that are popular today deep learning, and hence deep learning is just effectively a marketing term. Let's look at a diagram that I think will give you a fuller picture. Neural networks actually form a superset of deep learning. In other words, all deep learning is neural networks, but not all neural networks are deep learning. There are several types of neural networks that do not appear in modern deep learning literature. Some of these are very old, and people just don't take interest in them anymore. Some of them are just alternative models of the brain. Some examples are self-organizing maps, or SOMs. These are for unsupervised learning. RBF networks, which use a radial basis function. Spiking neural networks, which use spikes or action potentials, just like the biological brain. We have some teams that are trying to build physical neural networks using specially designed microchips that act like synapses in the brain. And if you guys are old enough to remember the Palm Pilot, Jeff Hawkins, the founder of that company, went on to start Numenta, which focuses on understanding the brain. They created something called the hierarchical temporal memory, or HTM. So you can see that there are many types of neural networks that are not part of mainstream deep learning. So whenever people tell me that this course is about neural networks and not deep learning, I find it really funny because this course covers exactly the subcategory of neural networks that is actually essential to the rest of deep learning. The best way to understand deep learning is through time. So all of these concepts are important parts of deep learning literature, and it's very useful to see them chronologically. At the beginning, we have the perceptron classifier. This was invented in 1957 by Frank Rosenblatt. As you may have heard, its inability to classify nonlinear patterns led to the AI winter. The perceptron classifier is related to another linear classifier called logistic regression, which is the prerequisite to this course. Unlike the perceptron, logistic regression is very grounded in probability and statistics. There are also some nice relationships to the biological synapse, such as excitatory and inhibitory connections, the all-or-nothing principle, and so on. Recall that we sometimes call the logistic regression model a neuron. The problem is, this is still linear, and so it has the same limitations as the perceptron. But as we've seen, a very reasonable way to make a brain is to connect a bunch of neurons together, which is exactly what we did. We call this a neural network. This is when algorithms like backpropagation were invented, which happened in 1986 by Geoff Hinton. After this time, people weren't really paying attention to neural networks and instead leaned towards probabilistic graphical models. It's funny because probabilistic models used to be the new thing, and neural networks were the old thing, and now neural networks are the new thing, and probabilistic models are the old thing. Some believe probabilistic models may make a comeback in the near future. During the 90s, some researchers never lost hope in neural networks and continued to study them, so that's when we got CNNs and the LSTM RNN. Of course, they didn't receive much attention because few people cared about neural networks back then. And now we fast forward to the 2010s, the era of big data and massive data collection, more computing power, and so on. This gave neural networks the right environment in which to flourish. Neural networks have the special ability to increase in performance as more data is gathered. This is opposed to some other machine learning models, which seem to taper off after a certain limit. This superior performance on famous benchmark datasets were what allowed neural networks to become so popular. And so people who used to ignore neural networks were now starting to pay attention. A good example of this is the computer vision community. At this point, we've hit a critical mass, and soon everyone started using neural networks. And somehow during all this buzz, someone came up with the term deep learning. So deep learning is nothing but a buzzword, which was assigned to something that already existed, which was a subset of neural network research. And not only that, but remember that it's a common misconception that CNNs and RNNs are deep learning, and feed-forward neural networks are not deep learning. Remember that all this stuff actually predates the term deep learning, and they are all a subset of the study of neural networks. In this lecture, I'm going to answer a question that I get from time to time, and that is, who should take this course in 2020 and beyond? In order to understand why I'm answering this question, you have to first understand how and when I created this course. To make this short, I created this course right around the time TensorFlow was initially released. For all intents and purposes, we can basically say TensorFlow didn't exist. In the original iteration of this course, I had a single plug-and-play example for how to create and train your own neural network in TensorFlow, which obviously you could take and plug in your own dataset and so forth. A lot of knowledge about how to do things in TensorFlow wasn't well known at that time, and in fact, the largest and most popular library was called Theano. This was the original deep learning library in Python, which was also able to take advantage of the GPU. It happens that during this time, the way to learn deep learning for most serious deep learning practitioners was to learn the theory behind deep learning, and then after that, go on to build various kinds of neural networks in Theano, namely CNNs, RNNs, and some unsupervised models called autoencoders and RBMs. This was how I originally set up my deep learning series of courses. So basically, you would first take linear and logistic regression to learn about some basic machine learning models. Then you would take this course to learn the main theory behind deep learning, which basically consists of backpropagation. Then you would learn how to code neural networks in Theano, and then you would learn about more advanced architectures. In my opinion, this is still the best way to learn about deep learning because it teaches you about the main architectures and also about some crucial aspects of both supervised and unsupervised learning. I've discussed this elsewhere in depth, so if you're interested in learning more, then check out the lecture, What Order Should I Take Your Courses In?, which can be found in the appendix. There are similar lectures in the higher level discussion section where I've included the previous iteration of this lecture called Where Does This Course Fit into Your Deep Learning Studies, as well as a lecture titled Who Should Learn Backpropagation in 2020 and Beyond. Clearly, the subject matter will be similar to this. So how have things changed today, approximately 4 or 5 years later? Well, many things have changed. If there's one thing you should learn quickly in deep learning, it's that this field moves fast. There are new innovations on a daily basis. TensorFlow, the main library that students incorrectly came to this course to learn, used to make breaking changes on a monthly basis. Obviously, I wasn't going to create a new deep learning course every month, since that would be absurd. Since the time I created this course, TensorFlow in its original form has come and gone. At the time I'm making this lecture, the main libraries are really PyTorch and TensorFlow 2, which is very different from the original TensorFlow. The way to learn deep learning hasn't really changed, but we've learned that there are different approaches that different people prefer. Of course, this must be the case since everyone has their own learning style. Some prefer the bottom-up method, where they learn the fundamentals and they take things step by step in a very logical order. For these people, things tend to make lots of sense because they build things up very naturally from the ground up. Some might mischaracterize this as the academic approach. Other people prefer the top-down approach, where they start with high-level APIs, maybe a few lines of code, and then slowly figure out what's going on as they dig deeper. Some might mischaracterize this as the professional approach, but again, this is a mischaracterization. Obviously, a professional is merely a person who was previously a student, and therefore there should be no difference between professional and academic, because anyone who is competent should be both. But for those people who take the top-down approach, they spend a lot of time being confused because they see the high-level API, but they don't really know how any of it works. So they need to constantly inquire, and more importantly, they need to ask the right questions. Asking the wrong questions or focusing on the wrong things tends to lead people astray, and I've seen this with my own eyes many times. One example of that was a guy who was really concerned with how TensorFlow sessions worked. Like he thought it was some integral part of deep learning. I told him no, it's just a nuance of the TensorFlow library. It's not actually related to deep learning. But he didn't believe me. And guess what? Today, TensorFlow sessions no longer even exist. So all that time spent worrying about the wrong thing was wasted time. Now, this is not to say I think one approach is better than the other. It may sound like I'm advocating for the fundamentals first approach rather than the top-down approach, but this is not true. I think people should do what they feel like doing. All I've done is describe to you the experiences of others, the experiences that I've observed, and the experiences that students have shared with me. Now, you must be wondering, how would I know this? The answer is, I did an experiment. I did an experiment on you, the students. You students were my test subjects. You see, today, I now have two types of courses. There is the original deep learning series, which takes the bottom-up approach. And now I have courses on PyTorch and TensorFlow 2, which take the top-down approach. In the top-down approach, what we do is explain a little bit about what's going on, and then dive directly into the code. The code is quite simple, so it doesn't take a lot of theory to understand, as long as you don't think too much. But what happens when you do start to think and you do start to ask questions? The answer, about 90% of the time, is that, well, you have to learn the in-depth theory. So what does that mean for you, the student of this course? Well, there are two reasons you may have come here. Reason number one is that you tried the top-down approach. You started with the high-level APIs like TensorFlow 2 and Keras, and now you want to know how it all works. Or you are simply the type of person who already knows that it's probably a good idea to start from the fundamentals. So this is great, you are in the right place. Reason number two is that you want to take the top-down approach, but you didn't realize that this course is all about backpropagation, which essentially means you're taking the bottom-up approach. If this describes you, then you're in luck because you have other options. If you don't like math, this course is not for you. If the question you automatically ask when you see math is, why can't I learn this using pictures or animations, then this course is not for you. If you don't have the discipline to spend a few hours or maybe even a few days doing a homework problem, then this course is not for you. Luckily, there are courses that are for you, the ones I just described. First, you can choose which library you want to use, either PyTorch or TensorFlow 2. PyTorch is backed by Facebook, and TensorFlow is backed by Google. The short story is that PyTorch is preferred by researchers and TensorFlow is preferred by more casual folk, which is why you'll see tons of blog articles using TensorFlow and Keras. At the same time, if you want to build anything more complex than just the three main architectures, which is ANNs, CNNs, and RNNs, you may actually find that this is harder in TensorFlow compared to PyTorch. High-level APIs tend to get messy as soon as you want to do something out of the ordinary. The main advantage of these courses is that they are newer. I was able to take the last 5 years of teaching experience and focus that directly on these courses. The result is the best learning experience I've created yet, although I don't have any plans to stop improving. In addition to that, they have tons more exciting and fun applications if that's what you're looking for. In addition to image classification, disease detection, and time series forecasting, we also look at natural language processing, recommender systems, GANs, and transfer learning. We even dive into deep reinforcement learning, and you will get to build a stock trading bot. Although it's around this time that many students feel they don't have the necessary theory to back up what they are doing in code, and thus need to take a step back and look at more in-depth materials. But as a responsible instructor, I do feel it is essential for me to explain that there are two available paths for you, so you can choose which one you prefer at the current moment. If you want to learn bottom-up, that's great. Continue on. If you want to learn top-down, I have excellent resources for you, and you can come back to this later. In fact, come back anytime you want. This course is timeless. TensorFlow 2 and PyTorch will eventually become out of date, but the fundamentals of deep learning will never change. In this video, I'm going to answer a question that I get from time to time and will probably get more and more common as time goes on. That question is, who should learn backpropagation in 2020 and beyond? First, let's start with the fact that I completely understand where this question is coming from. It makes total sense. If you are new to deep learning, you've probably come across some blog article showing you how to build an image recognition network in Keras, and you were probably amazed at how easy it was. You basically have state-of-the-art machine learning at your fingertips in a few lines of simple code. By the way, the Keras API is now standard in TensorFlow 2, so if you learned Keras before, then you're pretty much ready to go in TensorFlow as well. So after seeing the power that you can have with just a relatively tiny bit of effort, why would you want to do something like backpropagation, which is basically a giant and very messy calculus exercise? Especially for some of you who haven't done calculus in like 20 years, or even worse, have never done calculus at all. Now, I want you to think of this from another perspective. Why is the title of this course Data Science, Deep Learning, and Python in the first place? Well, I'll tell you that when I first started this course, not many people even cared about deep learning. I was the first instructor, I think, to ever create an online course and call it deep learning. I put data science in the title because back in those days, data science was still kind of a prestigious umbrella term that encompassed a lot of machine learning and statistics alike. Nowadays, the term data science seems to me to be a very cheap and insignificant term, as it's been co-opted by marketers and SEO experts. And people for some reason have combined data engineering with data science, which should be separate in my opinion. But that's beside the point. What I'm getting at is, this course was created so long ago that many of the libraries you know and love today, like PyTorch and TensorFlow, simply did not even exist. The inventor of Keras only just started working at Google. The TensorFlow library was only just released at the same time I created this course. So if you were ever wondering, why didn't this course use Keras or why didn't this course use TensorFlow, it's because they basically didn't even exist. In those days, backpropagation was still very much a central part of the deep learning curriculum. Anyway, that's just a digression, but maybe now you understand how this course came to exist in the first place. But why should you learn backpropagation in 2020 and beyond? In this lecture, I'll present to you two very common scenarios, which, if you encounter them, will pretty much be showstoppers in your deep learning journey. If I had to summarize these two scenarios, this is what they would be. Number one, your competition is learning backpropagation by the thousands. Thousands upon thousands of students are graduating with computer science degrees every single year, and it's only getting more popular thanks to machine learning. If they have these skills, but you do not, how will that make you look in front of your next employer? What other special skills do you have to offer that would make up for or even outshine the students who have graduated and are now entering the professional world that do know backpropagation and that do know the math behind machine learning better than you? Of course, you can't really answer this question confidently unless you truly know what knowing the math has to offer. You can't have an opinion simply because you don't like math or you're not good at math. Then your opinion is simply uninformed. You have no idea what your competition knows, and that is even worse. Number 2, eventually, your ability to understand concepts in deep learning and machine learning will diminish until you simply can't go any further. I'm seeing this all the time. I did a little experiment recently where I made a course all about deep learning using TensorFlow and the Keras API without any heavy math or backpropagation. What I noticed is that for students who have not learned backpropagation, their understanding of what's going on is severely limited. They're pretty much stranded in a place where their only option is to copy someone else's code. That's great and all, but do you really want to be a worker that can only copy code that other people have written? If I were your boss or your potential boss, why would I hire you when I could hire the guy who wrote the code that you copied from? Again, it's a matter of what are you bringing to the table that's better than what other people are offering? If all you can do is copy code, then you'll never be able to create anything new. You'll never be able to solve new problems, and other companies will always have a competitive advantage over yours, simply because, by definition, in order for you to copy something, it must have already existed somewhere else. Of course, I don't want to say any of this without concrete examples, so that's what's coming up next. Alright, so let's go back to the birthplace of deep learning, where this all started. Decades ago, Geoffrey Hinton, who I'm sure you're all familiar with by now, taught a course called Neural Networks and Deep Learning at the University of Toronto. Naturally, this course still exists. So let's see what these guys are up to. Well, it looks like, you guessed it, Backpropagation Lecture 6. So let's see what we've got in this lecture. Looks like some math, some more math, lots of math. Okay, let's check out homework 1. Oh look, deriving gradient descent update rules. Alright, maybe that's a fluke. Let's check out homework 2. Oh look, derive a sequence of vectorized mathematical expressions for the gradients of the costs with respect to W and B. Man, well, the lazy programmer can't always be right. This has got to be a mistake. Let's try one more time. Homework 3. Derive the backprop equations for computing. Oh man, well there you go guys. Gradient descent and backpropagation. As you can see, it makes up a pretty significant portion of the course. Now, I'm not telling you this to make you feel bad, that they know something that you don't. In fact, why would you feel bad? I'm giving you the opportunity to learn the exact same thing. In fact, a better opportunity, because I'm going to show you a lot of those tricky spots that you would be forced to figure out on your own in a stressful college setting. Whereas these guys have to do it for homework that is all by themselves, I'm showing you how to do it. So you have someone guiding you who's done it multiple times over. You are not being asked to do it all from scratch. Of course, it would be nice if you could, though. So the only way you would feel bad about this is if you rejected the opportunity to learn this stuff. In that case, it's your responsibility and not anyone else's. If you go to your job interview and they ask you, hey, why does everyone else know this but not you? What have you been studying? Oh, you decided not to study it because you didn't feel like it. I'm sure your next interviewer will be completely understanding. Okay, next. Forget about this college stuff. Let's say you've got a good, cushy job. No one is ever going to fire you because you're great friends with the CEO. That's fine. But there's another problem here. How do you do anything worthwhile in deep learning? Your simple 3 lines of code will only get you so far. You might even get to the point where you can write your own CNN or your own RNN, which are pretty easy nowadays. But if you want to go further than that, say with GANs or with natural language processing or with transfer learning, you can and you will get stuck. This is not a theoretical opinion. I'm talking about real examples from real students. I want to give you some examples, without naming any names of course, of how students who didn't have knowledge of the in-depth concepts were not able to progress in deep learning due to their lack of knowledge. Let's take one simple example to start with, CNNs. CNNs are neural networks that involve convolution. In fact, some CNNs have only convolutions. Convolution is a funny little operation from signal processing, but basically it involves a set of input features, as usual, a convolution filter, and then we convolve the input with the filter and that produces some output. For someone who knows backpropagation, it's obvious how those convolutional filters are trained. They're trained by using backpropagation. For someone who does not know backpropagation, it seems like magic. One of the most common questions I get is, how do we find those convolution filters? Well, we don't find anything. It's just backpropagation. There's nothing really more to say. So that's why it's kind of up to you to understand what backpropagation is, so that when someone says, these are just trained using backpropagation, you actually know what that means. Now, let me be clear. It's not even that you have to do the math by hand. That is not what I'm saying. All you have to have in your mind is the concept of backpropagation. That is enough to understand how convolutional filters are found. Another example I came across recently was with GANs. If you've never heard of GANs, just bear with me and pay attention to the high-level principles. Basically in GANs, you have two neural networks. One is called the generator and one is called the discriminator. Architecturally, you're going to hook up the generator's output to the discriminator's input, and the loss will be computed at the discriminator's output. During this time, the discriminator's weights are frozen, and only the generator's weights are updated. We can call these theta d and theta g. So when we do this, we only want to update theta g, but not theta d. How can we do that? Well, again, if you understand backpropagation, then this is obvious. Again, I'm not saying you actually need to do any of these calculations by hand. You're going to use a library like TensorFlow or PyTorch realistically. But this is not about that. This is just about your basic understanding of GANs. So conceptually, how you update theta g is obvious. You do gradient descent. This is just the chain rule. You take the loss with respect to the input to the discriminator x hat. X hat also happens to be the output of the generator. So by the chain rule, you take the gradient of x hat with respect to theta g, and this gives you the gradient of the loss with respect to theta g. This precisely describes how the parameters of the discriminator theta d do not have to be updated in this picture. Again, obvious if you know backpropagation, not obvious if you don't. So what's the lesson here? It's that unless you only plan on copying other people's code or using other people's code, you are going to need to understand backpropagation at some point. Even with the examples I gave you, it's not that you have to be able to sit down and work through all the mechanics. In fact, I skipped a lot of examples because I wanted to keep this lecture shorter. And it's not that every neural network you write is going to be from scratch. Clearly, that's not a practical solution to anything. But as you saw with these examples, it wasn't about sitting down and doing math. It was all on a conceptual level only. By not understanding backpropagation, even just conceptually, these students weren't able to grasp some of the more interesting concepts in deep learning, such as GANs. And let's face it, GANs are pretty cool. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we're going to discuss where this course fits into your deep learning studies. This is really important because deep learning is a huge topic. If you want to learn things in depth, then it's a good idea to understand how the pieces fit together and how they depend on each other. So what came before this course? What will you learn in this course? And what comes after? Well, what came before this course is basically everything that's listed in the prerequisites. The main prerequisite to this is logistic regression, also known as the neuron. This is really important because in order to build neural networks, we first have to know how to build a single neuron. A neural network is just a bunch of neurons connected together. But before neurons, it's helpful to learn about something even simpler, which is what I like to think of as the grandfather of all machine learning models, linear regression. Linear regression basically means just finding the line of best fit, which may seem trivial to you, but it introduces some important concepts. First, it introduces you to the idea that we're going to have some data, and we have a model that we have to fit to that data. In order to fit the model, we have to define a loss function, and then we have to minimize that loss function by taking its gradient. The loss function we usually use is the negative log likelihood. And so here we sort of have a marriage of some important concepts. First, where do gradients come from? That's something you learn about in your calculus class. Second, what is likelihood? That's something you learn about in your probability class. So calculus and probability give us some of the foundational techniques we need in order to solve machine learning problems. And we can apply them to linear and logistic regression, two simple linear models that provide the foundation for neural networks. So what comes after this course? This course is all about neural networks and how to train them. But once you've learned about that, then you can start using what you've learned as a basic building block for more complex applications. So you can learn about modern deep learning libraries such as Theano, TensorFlow, Keras, and PyTorch, which make writing complex neural networks a lot easier. One thing you'll also learn is that training neural networks takes a very long time. Think days or weeks. It's not a matter of going to get a coffee and coming back when it's done. It's more like you check back every morning to see the progress and go work on other things while you wait. So luckily, these modern deep learning libraries make use of GPUs, which, thanks to the gaming industry, makes things like matrix multiplication and other common deep learning operations orders of magnitude faster. So these modern deep learning libraries are very important. You can learn about specialized architectures such as convolutional neural networks, recurrent neural networks, recursive neural networks, memory networks, and so on. There are many different kinds of neural networks out there. You can start applying those specialized architectures to specialized problems, such as computer vision, natural language processing, and reinforcement learning. So this is an exciting time for deep learning because it's so useful in such a wide variety of applications. And that brings us to this course. Where exactly does this course fit in the grand scheme of things? Well, a lot of people like to take the abstraction approach when it comes to deep learning. They say, give me the API so that I don't have to worry about the details. This is okay if your problem is very narrow and nothing you need to do is uncommon. But the problem arises when you need to do something different or when things aren't working. Even the smallest change will confuse someone who doesn't know what they're doing. I've seen this with my very own eyes time and time again. If your problem involves anything other than directly copying someone else's code, you'll run into issues and you won't be able to solve them. So that's why it's important to actually understand deep learning on more than just a superficial level. Any random Python coder can copy a few lines of Keras code. That requires no skill and no thinking. And if everyone else can do it, then why would someone hire you specifically if you just have the same skills as everyone else? So what is this course about? This course seeks to explore the details of neural networks, the details that other people usually want to ignore to their own detriment. It's a more complex model than just linear regression or logistic regression, but it's not so complex that you need a specialized library to do it. One of the core concepts of this course is backpropagation, which is how a neural network learns. The principles of backpropagation are used to train CNNs, RNNs, and pretty much all popular neural networks in existence today. So that's why it's something worth learning about. As you'll see, it's nothing more than following the same principles used to train linear and logistic regression. In order to debug the training process, or to study more advanced additions to the training process that have been invented recently, you need to understand how training is done in the first place. If you don't have this, then you can't have anything that builds on top of this. So that's who this course is for. It's for those who understand why we want to learn these things, and for those who really want to understand how deep learning works. Let me also talk about who this course is not for. Incidentally, this course has become one of my most popular deep learning courses, although in my opinion, my newer deep learning courses are much more exciting. I've noticed that a lot of people end up signing up for this course without thinking, even though they were probably looking for some other topic. So I'm taking this opportunity to warn you that, if you are one of these people, you may want to reread the course description and make sure these are the topics you want to learn. So who is this course not for? This course is not for people who are missing necessary background knowledge. This course goes in depth and it requires knowledge of calculus, probability, and logistic regression in order to build on that knowledge. We can't build on knowledge if it doesn't exist in the first place. This is not like a pop science book or a For Dummies book. This is the real deal. Sure, it's possible to make things look easy, but then you have to question, what have you really learned? It would be like trying to learn quantum mechanics without first learning Newton's laws. Whenever I ask people, would you sign up for a quantum mechanics class without first knowing anything about physics? Well, let me tell you, nobody says yes. So why treat deep learning differently? They are both college-level subjects, and surprisingly, they both depend on a lot of the same prerequisites, namely probability, calculus, and linear algebra. Where they differ is that deep learning involves data and programming, whereas quantum mechanics involves physics. But you wouldn't sign up for a quantum mechanics class without knowing about Newton's laws first. So don't be surprised if you try to learn about neural networks without any background knowledge, that it will be incredibly difficult. Now, I'm not saying it's impossible. I've seen many people catch up and do well. But what I am saying is that you have to be mentally prepared to do the work where necessary. Another group of people who this course is not for are people who are looking to learn about more advanced architectures. If this is you, and you don't believe that backpropagation is part of deep learning, or you have limited understanding about the differences and similarities between neural networks and deep learning, please check out the lecture, What is the Difference Between Neural Networks and Deep Learning, in the appendix. This lecture was made just for you. What I find is common about this group is that they are not actually more advanced or have more advanced knowledge. They just want to learn about the most advanced architectures, but without knowing how the basics work. And that's probably why they are confused in the first place. So as an example, will this course teach you about convolutional neural networks? The answer is no. I have a course called Convolutional Neural Networks. Guess what that course is about? And by the way, do you see how the term neural networks shows up in convolutional neural networks? So what do you think will happen if you try to learn about convolutional neural networks, but you don't know how neural networks work in the first place? Same goes for recurrent neural networks, reinforcement learning, and so on. Okay, so it's really important that you read the course description so you know the difference and you have an accurate picture of what topics this course covers. You can't just read the title and assume that you know what this course is about, because a lot of people have misconceptions about what deep learning really means. I don't know how or why this particular course of mine has seemed to attract these students, but let this be a friendly warning that what you think about deep learning may not be 100% accurate. Okay, so hopefully this lecture helped you understand where this course fits in your journey towards becoming a deep learning master. You may also want to check out the appendix lecture, What Order Should I Take Your Courses In? It's not so much about my courses in particular, but just how all these different subjects fit together and depend on each other. So I hope this lecture gives you a better idea of not only what this course is about, but what this course is not about. So what I want to make sure is that this course is just right for you. In order for that to be the case, you can't be too far behind, but also you can't be looking for content that is far more advanced. If you're right in the middle, then that's perfect.